Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we're going to talk about numerics, in particular the so-called finite element and finite volume method. These are both very complicated and now very popular methods for handling unstructured domains. In the previous class, we talked about the transformation of the governing equations for structured grids, that is, from their physical space to a computational space. Then we looked at different types of finite differencing approaches, which we've covered extensively in this class. Remember, we looked at these for spatial discretizations. Later in the class, we'll look at time marching and time-dependent problems. We also introduced the so-called spectral method problem, or spectral methods, which is reliant on basis functions from Fourier transforms. You might see something very familiar with this approach when we talk about the finite element method. Today, we're going to focus on two major discretization approaches, the finite element method and the finite volume method. We'll look at the finite element method first because, of course, it's slight similarity to the spectral methods in that it uses a basis function. Note that both these methods are very extensive in themselves. For example, at the undergraduate level, often the finite element method has its own dedicated class, which is often required in many mechanical engineering departments. We're only going to be able to look at it from the surface today so you can understand its use in fluid dynamics. Unfortunately, what most students learn in the finite element method in their mechanical engineering curriculum is not applicable to the fluid dynamic equations because they would create unstable formulation. We'll see that in this class and introduce you to some stable formulations. They're extensive, and an entire class can easily be dedicated to finite element formulations just for fluid dynamics. Nonetheless, we'll get a slight understanding and big picture of how they work. That's important. Let's introduce some basic nomenclature of the finite element method. We'll do this for a simple one-dimensional problem at first, where we have perhaps a one-dimensional spatial domain. We are going to use the famous approach of Galerkin, who we'll talk about in a moment, where the variables of the partial differential equations will be approximated as a linear combination of basis functions. This is one type of approach. There'll be so-called trial, interpolation, and shape functions. There'll be local properties, which are then assembled in global properties. That is, each element will have its own local properties, and they'll be combined in some way to find the global properties, which corresponds to the entire solution. The local properties correspond to each element. Let's examine one particular problem here. On the left, we have elements in a particular domain. For example, our whole domain will be capital omega, and the boundaries will be capital gamma. The domain will extend from, say, 0 to 1 in this particular case. The entire domain, which we'll call overline or overbar omega, will be the union, that's that U there, of omega and gamma. On the upper right, we can define now some global elements. This is the domain itself, the original domain. We would discretize it with some distribution of grid points. Here we have two elements. We don't call these volumes now because it's a finite element approach. We'll call these elements E1 and E2. And the domain will have length L, and there'll be three particular nodes. The global nodes we'll call capital Z sub alpha. In the lower left, we'll have local nodes, Z sup E sub n. Here, n is the number of nodes per element, and E dictates that it is an elemental basis for the element Z. So now we've taken our elements from the global basis and divided them in each of their own separate elements. Now each element will have its own particular nodes. For example, E1 has the first and second node, and the second element has a first and second node. They have their own distances h. In 2 or 3 dimensions, this can be done in the same way. Now finally, in the lower right, we might define particular variables. If it's a one-dimensional problem, we might have a variable u. In each particular element, there'll be, say, variable u1 and u2. In the second element, we have u1 and u2. There'll also be a definition of u of x. So, in a sense, you can already see what we're doing, that we've taken the discretization and broke it up in individual elements. Based on the values of the unknown variable at the borders of the element, or boundaries, we can actually construct functions that fit those boundary conditions on an elemental basis. When we go back to the global domain, we would match the elemental interfaces. In this case, element 2 has node 1, which is coincident and should have equal values with, of course, element 1, node 2, right here. So u2 of element 1 should be equal to the velocity or value, of u1 of element 2. They should be equal because they're at the same grid point. Now, there's some formulations which do not enforce this constraint. They're called discontinuous. We'll look at the continuum formulation in this class for simplicity. You might ask yourself, who is Boris Galkin? Here he is on the right. In the upper right is a drawing, and the lower right is a picture. He was a Soviet mathematician and really an engineer at heart. So the finite element method was invented and put forward in the Soviet Union by this person here. He lived from 1871 to 1945, and fortunately he saw the end of World War II. He was trained and learned in the St. Petersburg Technological Institute, which still has descendant institutions today. He was a member of the Communist Party of the Soviet Union. Ironically, he was imprisoned by the same Soviet Union for protesting on behalf of the engineering union. So much for workers' rights in this case. In 1915, he published an article in which he put forward this whole idea of approximate methods for differential equations. And of course, he was involved with teaching at the Women's Polytechnical Institute. He's a fascinating person. I encourage you to read more about him online, because his basis is used in almost all parts of numerical methods now. It's a really amazing idea and has impacted our world. Let's move back to the formulation of the finite element method. The finite element model will be formed in omega, which is the union of the domain and its boundaries, in the first equation. We've already introduced this. We can also do the same thing to each element if we isolate it from the so-called global domain. Here, we have the same exact equation, except now we have sub e to denote it's the elemental basis. Each element consists of, in this set notation, of the domain of the element with the union of its boundaries. The domain and the boundaries make up each element. Very simple. The boundaries of the element and the neighboring element, therefore, are the intersections. So each particular element would have, of course, a shared boundary with neighboring elements, perhaps element f. So the intersection of the boundary of element E with element F will just be gamma sub EF. That's our notation. Finally, a finite element model will be the union of all elements. So the whole domain, of course, will be the union of all our elements. This is all just set-builder notation and standard. Here we'll define capital E as the total number of elements and omega bar as the global nodes and local nodes for ZA, which are the global known numbers. Now we'll use small z for local numbers and small e for local element numbers. You'll see these in the coming equations. You might want to make a note of them on a piece of paper. Now we can write these formulations in a matrix form as shown in the first equation up here. Recall the definition of Z1. Remember, it is the local known numbers. And we can write that out, for example, two particular known numbers for the one-dimensional formulation we just showed. On the right, we can show how the local nodes are related to the global nodes through these matrices delta sub n alpha for each element E. We can define these in this way. It's just a compact way of making this notation. N is the so-called free index in this case, and it'll correspond to the number of equations formed. Now, there'll also be a Boolean matrix with this property. This is this Boolean matrix which connects the local to global elements. It'll either have ones or zeros within it. It'll have a 0 if there's no connection between little z and big Z, of course. It'll be a 1, unity, if the local known number will correspond to the global known number, alpha. We can also write this in this following way. Z alpha equals delta of Zn. So we can do the inverse transform of it and write global nodes as a function of elements with each particular Boolean matrix. We can combine our definitions of Zn and little zn, and we'll find this particular relation. That is, if we multiply our Boolean matrix and its inverse together, we of course would get a Kronecker delta function. You recall the Kronecker delta function earlier in the class. Delta sub alpha beta will be 1 if alpha is equal to beta and 0 otherwise. It's a very simple way to find it. We can also do the inverse operations and find delta and m. This is one important property of the Boolean matrix that maps the local nodes to the global nodes. Earlier in the class, we talked about tensors and their use as a simple review. Here we're going to meet them again in finite element methods. The use of the tensor notation will indicate a free single index, which implies the components of a column vector. And this column vector will have a free double index where it denotes a matrix with its size determined by the range of the indices. Here, our unknown value u may be approximated linearly with a local element e, bounded between the range of the domain. Here in one dimensions, we might view that so-called basis function as nothing but an approximation which can be fit based on the solutions at the boundary. Here we see this in the first equation on slide 8. We'll write that u on an elemental basis is a function of x. So this is not a global solution. This is only a solution at each element. Will go as a basis functions times u of n in the element. So each particular element will have its own basis function. You can imagine that if we're in something more complicated like 2 or 3 dimensional domains, we would have to transform each particular element to a standard element. A line, a triangle, or a tetrahedral are very common transformations. Each one would have its own basis function. So here, just like in the spectral approach, we are rewriting our solution in terms of this basis function. This is part of what Galerkin did to decompose these domains that are very complicated for structural problems, not fluid dynamic problems. Here we define capital phi sub n sup e of x. This could also be a function of x, y, and z, mind you. Here it's one-dimensional. We'll show formulations later in this class. Here we'll say that the basis function is bounded from 0 to 1 for each element. And that means it's just a standard element. If we have an element of a different size, we can use a transformation, just like the Jacobians of structural methods, to transform it into a unit element. That's pretty straightforward. Then we'll also impose that if we sum the basis function over each element, it will be equal to 1 at each particular node. For example, at one particular node, in one dimension, we might have 2 basis functions per element. At each particular node, the summation of their values should be unity. This is our restriction, and it's almost universally used. Finally, phi with each element z will give us the Kronecker delta function of nm. The local values of the nodes will be related to the global nodes easily through, of course, our Boolean matrix operation, which we just found. You can see now we've shown the major picture of the Galerkin finite element approach, that we're taking our domain, splitting it up into elements, then we form basis functions, which are chosen by us, it's our choice, which have these certain properties. We then find the solutions on each particular element, given the boundary conditions and connection between each element, and find the solution based on the basis functions and reproject it back to the global domain. That's the process of the finite element theory in a nutshell. Let's now look at some basic basis functions. Now, think of the finite element method as a way that instead of directly finding, say, velocities and pressures and other field variables and unknowns, that we're simply looking for the magnitudes of the basis functions, as they are representative of the solutions. The Galerkin approach, for this reason, is viewed as the weak solution of the equations of motion, not the so-called strong solutions, which are found from more direct methods. In this weak solution, we might now have to illustrate the properties in one dimensions at least, to illustrate the method of the basis functions. Let's do that now. On the upper left, we have a so-called linear interpolation of the basis functions. There are an infinite number of basis functions that hold the properties that we showed in the middle of slide 8. Here we have basis function. Recall at the boundaries, the summation of the basis function should be 1. So, in a one-dimensional element for element 1, we could say the most simple basis function would be linear. And there'll be 2 basis functions because we have 2 nodes in this case. We'll call the first basis function phi1 for element E and the second basis function phi2 for element E. Their summation, phi1 plus phi2 at both nodes, as you can see, will be unity, as denoted here. And each basis function will be 0 at the corresponding nodes that are not its own node. We can define this linear basis function the simplest way. Say the element has a length h. On the right, we can say for node 1 to n, where n is 2 in this case because it's a one-dimensional element, we could say that phi1 goes as 1 minus x over h, and phi2 goes as x over h. These are two linear equations. Now you can stop and think that polynomials of any particular order can also, if they're carefully formulated, have these properties too, that the summation of the elements everywhere in the domain will be unity, especially on the nodes. So the summation of these two basis functions, with that is their prefactor, will give some kind of solution that's reconstructed of, say, u in this particular problem. This is the local interpretation of the basis function. On the upper right, you can see a global interpretation. For example, now we have 3 nodes that are global and 2 elements, and each element has its own 2 unique nodes, and it also has its own unique basis functions. So, for example, if we're only looking at node 1 in the first case, we might view that the basis function is 1 minus x over h. In the third case, we're looking at the basis function of the second element and second basis function. In the middle case, we show how the basis functions are connected for 2 elements using the second basis function of element 1 and the first basis function of element 2. You can see that through this process, we can essentially construct any type of solution over this domain by varying the magnitudes of the coefficients of these basis functions, which is what we're really solving for in the finite element method. You might also increase the number of grid points, and you can reconstruct any type of function. You'll note that in this formulation, the functions we can construct in the global domain would be continuous, but that's only because we've imposed a constraint that in particular nodes we only can have one solution. That is, the solution at, say, node 2 is equal to the solution of node 2 from element 2 and element 1. Finally, down at the bottom, we can try and connect the idea between local and global values. If we're multiplying these basis functions by our solution, which is essentially the coefficients, magnitudes of the basis functions with time, then we would have a local solution and a global solution. The local solution, of course, would be constructed on each element. For example, in E1, we would now have U1 and U2 at nodes 1 and 2 respectively. At element 2, we would also have U1 and U2. We would then have to combine these with a simple algorithm, which is shown mathematically down here in the lower right-hand corner, of course, the global solution. So we would have to map each element to the global solution. For the total number of elements, E, capital E, the global functions will be written as the union of all local element contributions. This is alluded to these equations down here for these particular 2 elements. We can write that as simply of U equals phi of sub alpha of U sub alpha. That is, U is nothing but the union of all elements of the basis function for all elements times that Boolean matrix operation times, of course, the velocity alpha for each element. Now, here we define something new, which is phi sub alpha. This is the global trial basis function. This is useful in some formulations. So phi sub alpha will be the union of all the basis functions with all the Boolean matrices. So this can be found because we already know all the Boolean matrices for each particular element, and we can already know the basis function, which in this case are just linear functions for each particular element. We have the union of all these from all elements, and we would find phi sub alpha, which you see in the definition for the U, velocity perhaps, which connects the velocity from all the elements. This is a very complicated way of writing it, but you can just imagine that we would just take the union in the algorithm for each basis function with its Boolean matrix, and then of course multiply through by U for each particular element. And we would have our global solution. This is done in a discretized approach in the computer. So we'd of course replace our union with a summation that is this loop, like a for loop or do loop in a computer program. So now we have our major preliminary definitions for the 2 approaches which are possible. And there's 2 major ways to formulate finite element methods. The first is called the variational method, which minimizes some principle of the governing equations. The second is called weighted residual. You should always know which type of method your finite element solver is using. The second method, the weighted residual, will try and minimize the error of the residual of the PDE. And we'll talk more about residuals later in this numerics part of the class. Typically, for the second classification, we would have some sort of subspace which spans the test function of W, which will project the residual R into a subspace. And this is what we call the inner product process of the residual. We define that as down in the equation at the bottom of this page and 10. Here, W will be the weighting function. This is really our choice of what the weighting function is. This means that the error at each point within the domain will be orthogonally projected onto A. The functional space spanning by the weighting function summation of the entire domain will be set to 0. If we choose test functions W alpha, which will be replaced by basis function, then the scheme is known as a Galerkin method. So you can imagine that there are particular schemes with weighting functions where the basis functions, in the case we discussed, would be those linear equations over a one-dimensional element, then it will be known as the Galerkin method. So this is the key point. There can be formulations which are not traditionally Galerkin, but this is just his formulation, and others grew from it, which didn't make this assumption. Let's try and illustrate all this with a single PDE that's very simple so that it can be more understandable. Let's look at the single differential equation d2u dx squared. That's the second derivative of u in the x direction minus 2 is 0 over the domain of 0 is less than x less than 1. So this is a very simple case. It has nothing to do with anything. It's just to illustrate the purposes of the problem. Now, the global Galerkin integral will then be phi of alpha. Remember, we defined phi of alpha in the previous slide. This is the global trial basis function with R. This is going to be the residual of the differential equation. So if you look at this equation, we have d2u dx squared minus 2 is 0. The right-hand side will be R. You can see we would not set R equal to 0 because in the numerical scheme, what is discretized by the computer, there will be some error. So this is the equation we're trying to model and solve numerically with the finite element approach. But of course, a numerical solution will have some error. That error is called the residual. So in the numerical solution, we'll have d2u dx squared minus 2 equals some value. And that value, non-zero value, will be the residual. It is the error in the solution. So we can write out this operation. We can write the integral from 0 to 1 over the element, in this case, over the domain, of phi of alpha of our residual of our equation. So the residual is equal to the equation, of course, itself. So we'll write d2u dx squared minus 2 of dx equals 0. Now we would want to try and use the variational approach to solve this. To do this, we can take this integral equation and integrate by parts, which is something hopefully you recall from Calculus 1. If you perform integration by parts, you'll find this particular equation. Let's try and manipulate it further. So recall that phi alpha is the global boundary test function. So that is indicated by the sup star quantity and is defined at x equals 0 or 1, the boundaries of the domain. If we substitute u equals phi alpha u alpha, which is how we're projecting and defining the weak solution, recall, way back in the beginning of this derivation, into our integration of parts, we'll find the following equation here. It's slightly simplified, but you can see now we have a Newman condition at the boundaries. This bar at 0, 1 represents the boundaries of the values of du dx at the boundary, with, of course, the global boundary test function at the boundary. We have these remaining terms as before. We call the left-hand side of this equation the so-called weak form, and that's because it finds weak solutions. The solutions are considered weak, which is kind of slang in math almost, in the community, especially in engineering, because we're not finding u directly. We're writing u as the basis functions and trying to find the magnitude of the basis functions with time, or if it's time independent, just the basis functions themselves. We can write this equation up here in a very compact way, which might be familiar to some people who've taken a finite element method class. But for now, let's try and explain it. We'll write it as k alpha beta of u beta equals f alpha plus g alpha. The reason we wrote it in this way is many types of differential equations can be formed and compacted into this particular way for k, f, and g. Here, we'll define k alpha beta as the global stiffness, diffusion, or viscosity matrix. F will be the global load or source vector, and g will be the global Newman boundary vector. These are named for very physical reasons. F will be like a loading or forcing term, or source term in the equation of motion. G will be the Newman boundary condition on the boundaries of the domain or elements, and it'll contain all the other major physics and parameters and coefficients of the problem. You can write these out for this single differential equation in these equations at the bottom of the slide. In the interest of time, take a few moments and review them, especially the formulation on the final on the right-hand side. You'll see that these elements are connected to the global matrices and vectors through the same type of Boolean matrices, multiplied through their unions, which would of course be written as loops or summations in a computer code, with their local stiffness, boundary, and source matrices and vectors respectively. Now, let us talk more about the Newman boundary interpolation function. These can simply be written as direct delta functions about z of n. We'll apply phi of n for sup star for each element as 1 if the Newman boundary condition is applied to a particular node. Otherwise, it will be 0. We will then assemble the global system as shown at the second equations on this slide. This is basically enforcing the boundary conditions of the global problem, not on a per element basis. An interior element would of course not have a particular boundary condition because it's not on the boundary of the global domain. Its boundary conditions are simply that it is exchanging information with neighboring elements in a very physical sense and explanation. These conditions enforce the boundary conditions that are Newman or Dirichlet or whatever you want to specify on the boundary of the entire domain. It's important to kind of keep these separate in your minds, that we are now talking about what's happening on a local element level and also a global level. These boundary conditions, in practice, of course, are enforced on the elemental level in the actual solvers. We can now write out all these stiffness, source, and Newman boundary vectors very compactly for this particular problem. And here they are for this one-dimensional simple ODE. You can see and imagine that writing these out for the full Navier-Stokes equations, which are now a linked set of PDE, is very complicated. It's very rare for a practicing engineer to go through this process. And all this is done in advance by research teams and computer scientists and mathematicians and the physicists and engineers working and developing computational solvers for finite element methods for fluid dynamics over the course of many years. If you want to write your own finite element solver, I strongly encourage you to try the one-dimensional problem first for simple compressible equations. Then you can extend it to 2 and then 3 dimensions. It's really the only way to do it, and it's very difficult to write a fully 3-dimensional solver without practicing the one-dimensional case first. That's just good advice for new people to CFD who really want to learn how to do this. I encourage you to try the one-dimensional formulation yourself and try and recover some of these coefficients. Let's try and extend our work to the so-called multidimensional problems. That is where the dimensions are greater than 1. They might be 2, 3, 4, or even more. These formulations have been performed for all kinds of different equations. In particular, for an example, let us look at the so-called Poisson equation, which is of course the Laplace equation with a right-hand side source. Here we'll define the residual, that is the error in the equation, of the Laplacian of u minus f is 0. The equation we're trying to solve is the Poisson equation, which is written as nabla squared u minus f is 0. The residual, of course, is equal to these forms. Remember, the residual itself you want to drive to 0. For the residual formulation, we would want to minimize that in the solver through the finite element approach. Let's look at this application. On the second major equations of this slide, we'll follow the one-dimensional approach, but now, of course, in multiple dimensions. And we seek to find the matrix K and the vectors f and g. So we would write our residual equation with its inner product of phi of alpha. Phi of alpha, remember, is simply the basis function of our solver. But now this has to be written in 2 dimensions or more. In 2 dimensions for linear finite element solvers, which are working on triangular elements, we would have planes. And planes would satisfy all the conditions of the basis functions, which we showed earlier, but extended in 2 dimensions. In 3 dimensions and higher, you would of course have basis functions that are perhaps something a little more complicated, like tetrahedrals and higher order dimensional elements. It's good to take a trigonometry class or a higher order geometry class to understand this. We would then go through and integrate by parts. Here you can see the familiar boundary conditions, which is an integration over gamma of each particular element. These, of course, are very important at the boundaries of the domain. Then you'd have the 2 other terms which are equal to 0. We've replaced our residual, of course, with the Poisson operator itself in the equations before integration of parts. Then you can take this equation just like we did before and put it in the same familiar form of the matrix K operating on U, the unknown, with right-hand side vectors F and G. Here you can see we formed a linear set of equations and discretize them a finite element. This in practice results in the same form. It's a linear algebra problem, so it'd be like AX equals B. Instead of AX equals B, which is familiar to most students, we have KU equals F plus G. We can solve this with the same linear algebra solvers that are developed in linear algebra classes. And we'll talk about those later in this section, the linear algebra solvers. So these can be applied, of course, for linear equations. The Poisson equation, Laplace equation, etc. are all linear equations. So we have to make sure that we use a linear solver for them. If we have a nonlinear set of equations, for example, then of course the formulation becomes much more complicated. But this is the basis of the finite element method. Here, of course, we can write the right-hand side of K, F, and G in a very general way for the Poisson equation. We've defined all these variables on the right-hand side. Here, these unions in the solver would, of course, be approximated as summations, and the integrals would be performed numerically after simplification with the basis functions on some trial elements, which are simplified and transformed from maybe a skewed element or a rotated one. Unfortunately, these basis functions, the traditional ones of Galerkin, for fluid dynamics problems will lead to unstable solutions. That is, if we follow this exact same approach for the Navier-Stokes equations in, say, 2 or 3 dimensions, and we try and solve them, the solutions will diverge, they're unstable, and we will not find numerical solutions which correspond to the original differential equations. This is where it gets really complicated, and there's specialized choices through all these formulations for a finite element to try and simplify this approach and get a stable solution. Typically in fluid dynamics, we'll use a specially selected basis function. The choice of the basis function is ours as long as it satisfies our original properties. The most common selection is the so-called Galerkin test function, also named after Galerkin, plus a numerical diffusion test function. So we take the original in the simplest formulation, basis function proposed by Galerkin, which just might be linear and coarse, and we add to that basis function a numerical diffusion test. We'll call that psi of alpha. So now our new basis function is phi, which might be simply linear, plus a diffusion test function. In a sense, we're adding a little extra diffusion to the flow to keep it stable. We can rewrite this with the inner product of the diffusion and traditional Galerkin basis function, phi alpha plus psi alpha, with its inner product with the residual. Here the residual would be, say, the residual of the Navier-Stokes equations or Euler equations or any other set of fluid dynamics equations. That would be rewritten as the integral over the domain of the basis function plus the diffusion test function with the residual, and we'll set it to 0. This is the basis of all, well, not all, but most finite element solvers in fluid dynamics. I've listed a few different types of formulations which are most used and famous today. For example, the streamwise upwind Petrov-Galerkin formulation. I guess I listed that because it's one of my personal favorites, which I programmed as a master's student and PhD student. A Taylor-Galerkin formulation, the generalized Petrov-Galerkin formulation, characteristic Galerkin formulation. What is probably most popular today in research is the discontinuous Galerkin formulation. This is exactly like the one shown, except we're not really forcing the values of U to be the same across elements. This way, discontinuities like shock waves can appear in the flow and they can be accounted for. And of course, there's so-called flow field dependent variational methods. You're welcome to look up any of these on Google Scholar and get overview papers if you wish. They're all very complicated and mathematically intensive. But if you choose one, it might be most fun to look at the discontinuous Galerkin formulation. The streamwise upwind Petrov-Galerkin formulation is also excellent numerically for high-speed flows because, of course, it builds an upwinding scheme. That means that it essentially reduces to a stencil which has upwind bias. That is, there's more grid points or information in the equivalent finite difference approach in the upstream direction, that's the direction where the fluid's coming from, relative to the downstream direction. Let's now turn our attention to the finite volume method. The finite volume method is much more direct and uses and approximates the integral equations. That is, their volumetric and spatial surface integrals across the domain, and discretizes the equations and the finite volume grid directly. Here we're looking at volumes instead of elements. This is a direct approach. It does not form like a Galerkin or basis functions. They aren't used at all. And many students are much more comfortable with this because, of course, they use volumetric methods like Reynolds transport theory in their undergraduate studies. First, recall that the governing equations are the Navier-Stokes equations, which we discussed earlier. Our goal is to form an integral discretization of those equations from the Navier-Stokes equations, just to illustrate the method itself. Here, we will formulate the control volume methods by taking inner product of the governing partial differential equations with some unit function. We'll call that script bold I. This operation will yield in the spatial integration of the governing equations. That is, still we'll have a system of equations corresponding to mass fluxes and all kinds of different operations of fluxes and volumetric sources. We will no longer need to coordinate transforms like we did in the finite difference approach, thankfully. And that's one advantage of this approach, is that there's no so-called coordinate transform. We can simply formulate the finite difference method directly on the grid from the integral equations. This is a major advantage. Unfortunately, you'll see it's very difficult to recover high-order finite volume approaches, which you can do trivially with the finite element or finite difference approaches. We'll designate the components of these normal vectors with the surfaces in the finite volume method, and this will accommodate unstructured grids. So finite volume methods were designed and are probably the most simple approach to program and understand for an unstructured domain. You'll also see it has the advantages of reducing to the finite difference approach if we use a structured grid. That's a fascinating property. There's two types of finite volume methods. There's node-based and volume-based storage. A node-based scheme stores values at each nodal point within the computational domain. A volume-based storage scheme uses the volume centers. That stores the fluid dynamic solution at the center of each volume. The solvers are typically written either way, and there's advantages and disadvantages to both approaches. Perhaps the biggest advantage of the volumetric approach, of course, is that it will store the solutions at the middle of the volumes and have less memory requirements, but you'll have less knowledge of the solution because you only know the solution at each particular volumetric center. Wow. Let's now look at one particular formulation. And you'll recall, if you go back to our fluid dynamics section, we talked about the form of the Navier-Stokes equations in the volumetric form. We've written this in our first line. Here, the vector form of the Navier-Stokes is shown. Partial u, partial t, time-dependent partial derivative, of course. And u will be a vector of the unknown variables, say rho, rho u, rho v, rho w, and perhaps an energy. F and g will be additional vectors which contain all your flux terms and everything. B will be your right-hand side, which is subtracted from both sides to move to the left. This whole equation, of course, is set to 0 because we want it to be 0. So it satisfies the Navier-Stokes equations in this vector form. And then we can set it to R, which is the residual, which is very familiar and like, of course, the finite element approach. You don't have to start here. You can actually start with the volumetric form of the Navier-Stokes equations. But this is how you should find them formally from the differential form. Now we would take the inner product with that vector I, which I discussed earlier. We can rewrite the right-hand side as nothing but the integral of the residual will be equal to 0. This is a very simple step, but this is the formal process to find it. Now, we can also find alternative forms about the volumes and surfaces. We can split this up through vector calculus and the theorems of Odrogorski in green, into two integrals about the volume, which is the first one. This is a volume integral of the whole domain of omega of partial u partial t minus b, which is the right-hand side vector, plus the fluxes through the domain. There's these flux terms. This is a surface integral of f and g. So there's the flux of f and g plus the changes of the field variables in the domain minus the source vector will be equal to 0. So this is still satisfying the same set of equations, and we haven't really made any assumptions at all. Here, n is the outward pointing normal of the domain or a particular volume element on the boundary surfaces. So we need to discretize this in some form, and it's very simple. We might just say that each volumetric surface integral equation here, we can have this equation satisfying each volume element, and we will sum all of them over all discrete nodes or cells through the control volume and control surface, CV and CS respectively. This discretization can be done in one simple step. Here, instead of an integral, we'll have sums of the volumes or the surfaces for each node, for each volume. And we'll take the partial derivatives and rewrite it as, say, delta u over delta t. So delta t will be our time step between different times, and delta u is the change in solution over different times. The source vector remains the same. So do f and g. But now f and g are being evaluated discretely over each control surface for each volume of the unstructured computational domain. We've replaced d omega with delta omega. This would just simply be the volume of each particular cell or volume, and d gamma with delta gamma, which is of course the surface area, and equal to 0. You can now see we are formulating a summation over every volume element to form a system of equations. This is really the final form of the volumetric approach, and it's the simplest approach of all. Perhaps you do understand and prefer the finite difference approach more, but this is really a personal preference. Many students getting into CFD for the first time prefer the simple approach. Anyway, we strive to find a system of algebraic equations for this discretized set of control volumes and control surfaces. It's pretty straightforward, and there's many ways to do it. The conservation of all variables will be enforced across all control surfaces. That is, the flux from one volume will be equal and opposite to the flux to the next volume of all the conserved quantities. It is enforced directly. It is not a weak formulation like the finite element. Therefore, when a quantity is transported, like mass, from one control volume, it is exactly moved to the next one in neighboring. No losses occur except for the error in the computer itself due to numerical error. That is the truncation of these problems numerically. There will be no creation or destruction of conserved variables. So the finite volume method is very, very popular in, say, the petroleum industry because there's no losses and accountability of the product is perfect. Even with very coarse volumes, you could have a control volume and computational domain consisting of one element or volume. This is exactly what you've done in your fluid dynamics or aerodynamics classes before you took this class. That is, you have used Reynolds transport theory and you've essentially discretized and solved numerically using the Reynolds transport theory, which is like a volumetric reduction of the Navier-Stokes equations. You can also imagine just simply having and cutting your domains in half again and half again to discretize your domain into smaller and smaller parts. That's one major advantage of the finite volume approach, is you are conserving all your variables and they cannot be lost. This is unlike the finite element approach, which is probably superior in many ways because of its higher order of accuracy, but it's only giving you a weak solution. And it's not going to likely, in some cases, if it's poorly used, guarantee without a doubt the lack of loss, that is, or the accountability of the finite volume approach. So, an advantage of the finite volume approach is that the governing equations will contain exactly and directly their physical interpretation, rather than distorting their physical interpretation through the use of basis functions or abstract finite difference approaches, which are designed to only retain some abstract quantity of the fluid dynamics, like the dispersion or dissipation characteristics. These are very abstract relative to very direct quantities like conservation of mass, momentum, and energy, which is what the finite volume approach is great at doing. It is also cost-effective because the flow calculations at each surface will need to only be performed once for each control volume. This is a wonderful thing and also an advantage over the so-called finite element approach. It is also less costly than, say, finite element approaches. It's easier to program. And it's algorithmically simple, as we showed in this whole approach in 1 or 2 slides max. And generally, there's only going to be 2 types of finite volume approaches, which you already discussed. And they're only classified into nodal center or cell-centered. And you should always know your solver if it's node-centered or cell-centered solutions. That way you know where your solutions are at. It's that simple. Let's now look at one finite volume approach, and we'll choose node center for now. We'll look at volume centered later. On this slide 21, we've shown 2 graphs. In the upper right, we show the entire domain. There's nodes which are numbered from 1 on up to 14, and there's a number of volumes. At one particular node, if it's a nodal approach, recall that we're formulating our volumes and finding solutions at the nodes. For example, at node 1, it has surrounding volumes A, B, C, D, and E. You can see another wonderful thing about the finite volume approach is that there's no restriction on the number of faces or sizes or shapes of the elements. It is good to have a well-made computational domain for a well-behaved solution, but these types of formulations are going to guarantee that you can create a system of equations that is simple, and you don't have to do a lot of extra programming and mathematics like in the finite element method to handle these arbitrary element shapes and their transforms. There's none of that involved. What a wonderful thing. But of course, all the simplicity will come at a cost, as we'll discuss later. Now, if we pull out node number 1 with surrounding elements A, B, C, D, E, F, you can see that these elements A, B, C, D, and E, there's an F, will have corresponding fluxes. On the element edges around 1, where my cursor is moving, there'll be corresponding normal vectors across each face. For example, from element C to whatever this element is here. Where is my cursor? We can label that later. It doesn't matter. So this node will have these connecting nodes also. 5, 7, 9, 11, and 12. You can see that in this set of equations. Now, we would also pull out that particular element and find, for example, in elements A and B, as an example, the corresponding normal vectors along the elemental face. You can see that one-to-one pull out. Just like we did with the finite element approach, let's try and solve a simple linear PDE on this 2-dimensional grid. So you can see it's very heavy in geometry. Here's our same Poisson equation. That's the Laplacian of u minus f is 0. You can see we have a residual. The residual will be uii, that's partial to u partial x squared plus partial to u partial y squared minus f is 0 for I equals 1 to 2, index notation. The residual is the left-hand side. We take the inner product to go from a differential form to an integral form. If you desire, you can already start with the integral form, and these equations are well known as much as the original PDEs in their partial differential form. Inner product is, of course, the integration over the surface will give you the integration of f, your source term, in each volume. So we have already written our differential equation, PDE in this integral form. We have flux terms over the surfaces will be equal to some source terms over the volume. Now, just like we showed with the vector form of the Navier-Stokes equations, we can put it in a vector form, not a vector form, but a similar form, where we have a summation over the control volume, which is the right integral summation. See, integral is summation, so we're just approximating the integral numerically, with the left-hand side of the fluxes. The fluxes will be over all the surfaces. And in this case, for the element we chose, the surfaces, of course, and elements are A, B, C, D, and E, and those are the control surfaces. We discretize the integrand of the integral, and we'll get delta u over delta x of all the normals plus delta u delta y over all the normals. So this is the change of velocity between the volume we're looking at and the neighboring volumes over each control surface. Delta y and delta x, of course, are the approximations of the distances between the centers of each volume. It's so straightforward and geometric. You can look from this slide on the right to the next slide and this equation, and you can match it up one for one. Try it out. It should be super straightforward. We can now take this equation and discretize it with the values of u between each volume and their surfaces. That's what this equation here is. It's simple geometry, and you can program this in a computer in a very algorithmic way. We'll have, for example, the first term is u7 minus u1. That's the delta u term. F7(1) is, of course, defined down here. F7 1, or Sij in general, will represent a surface parameter which is determined from the directional cosines. This is exactly approximating the surface areas across each, or in this case, the length of the lines between each volume. In 3D, of course, they're going to be surface areas, and it's going to be a little more complicated. But it's going to be nothing but simple trigonometry derived from cosines and sines, directional, that is, excuse me. So that's the whole formulation. And so this would actually be one equation which is conserved at each particular volume. If we have the Navier-Stokes equations, which would be 5 plus a gas law, would actually have multiple equations and fluxes written. So we might have 5 equations in 3D written across and for each volume. So if you have 10 volumes, you would have 50 equations found from a Navier-Stokes system. If you have 10 volumes for the Poisson equations, you'd of course have 10 of these equations. After you write them down, you would of course have to go to the boundaries and set the fluxes to 0 if, for example, there's no flux, or specify a flux on the boundaries of the domain for each particular volume if you would want to enforce like a Newman or inflow boundary condition. Now you can see there's one downside of this approach, and you would have to correct it algorithmically through detection, that is, if statements within computer code itself. For example, some of these directional cosine operations shown down here could result in major problems like divisions by 0 or 0 divided by 0. This slide is simply explaining, it's really a detail of how to correct those types of problems in a grid. For example, between node 1 and 9, where there's a vertical connectivity between node 1 and 9 for a node-centered problem, one of these cases would occur, and there'd be a singularity which we would have to correct. This is one example of this correction on the left. What we haven't done is look at the finite volume method or cell-centered approach. Let's briefly talk about this here, but it's almost exactly the same as the node center, except we think about the volume centers. We do not select each node and formulate a finite volume approach. No, we just select each volume itself and say we know the solution in the center of the volume. This reduces the number of equations formed and will be a cheaper solution to find and use less computer memory. Of course, the price is that it has less accuracy for the same type of grid, because you're essentially having less equations and less discretized form of the equations. So we'll define surfaces between each adjacent node. That is, the connectivity will represent the surfaces of the control volume. This is the most direct and understandable way. The nodal way is a little more complicated. Anyway, we can go through the same process for the Poisson equation and write down our discretized form, just like before, except this is centered around control volumes, and of course, the control surfaces around each volume is shown in the lower left. The surfaces and volume for perhaps volume ij is shown where my cursor is right now. We can also find corresponding normal vectors and surface areas. These all just directly go into our formulation, and we write it out as a linear algebra problem for the Poisson equation. It might be more complicated in a curvilinear grid. It's structured or unstructured, but it doesn't matter because we can easily handle any number of faces or volumes directly with this approach, and there's no transforms made. That's really easy and quite a fun way to do things. Here, once again, just like previously, we have expanded out in the discretization for one particular approach using the directional cosine and sines. This is fairly straightforward, and I'll let you review this on your own. But it's very much like what we've done before for the nodal approach, except it corresponds to the volumetric approach now. Take a second and review this slide. We've done all these formulations for finite element and finite volume in one dimension or two. You can imagine how difficult it is to extend a finite element approach to 3 dimensions because the complexity of the basis functions and their transforms of elements to, of course, some standard element. In the finite volume approach, we don't have to do these transforms at all. And the transformation of the finite volume approach from 1 dimension to 2 dimension is much more straightforward. And that is only because you are simply adding additional surfaces in 3 dimensions and accounting for, of course, the 3rd dimension and grid and connectivity, which can be handled easily by grid generation software. So for 3-dimensional problems with unstructured geometry, the storage of the faces and the volumes and the nodes and connectivity is the same, but of course it's always critically important. We can consider 2 domains shown for finite volume approach in 3D. In the lower left, we might show one particular domain. For each of these nodes, if it's a nodal approach, we would have to identify the corresponding control surfaces. This is trivial because the surfaces of the control surfaces are just defined by the nodal center of the connectivity of the neighboring volumes. This is shown for node number 10 pulled out from the domain in 3D. So this is exactly like in 2D but in 3D, and we have to simply identify extra faces and nodal coordinates that correspond to the third dimension. Algorithmically, it's trivial to do with a computer and much easier. Thankfully, we have digital computers now that can do this. I'm sure that you can devise a simple and easy way of calculating these facial connectivities and find the volumes and facial areas of the domain control volume or surfaces for each element or volume center as you go through the process. Let's now summarize what we've done today. We have discussed two of the major methods for discretizing unstructured computational domains. There's a few more, but they're very rare and almost never used. One important one is, of course, the finite element approach. Remember, the finite element approach, the Galerkin approach, invented by Boris Galkin, is taking and solving the equations on an elemental basis with basis functions. It is finding weak solutions numerically. Only specialized finite element methods, usually the simplest one, is the Galerkin formulation with a diffusion term in the basis function, are used in fluid dynamics. Do not take a finite element formulation that's simplified for usually structural problems and apply it to CFD. You're going to fail because it's unstable numerically and mathematically. The finite element method can easily be extended to higher dimensions. And we haven't done in this class, but you would just have three-dimensional basis functions or higher. And it can easily be extended to higher order of accuracy solutions. In fact, the finite element formulation can easily find the highest order of accuracy solutions than any other approach because, of course, all your basis functions are local to a node. If you wanted to find a high order solution with a finite difference approach, then you would have very, very large stencils. For example, a 40 or 50th accurate approach might use a stencil of anywhere from like 75 to 100 grid points. That's humongous and not practical, but has been done in research. That's why the finite element approach is so favorable today, because it can handle very high order of accuracy and find solutions that way without extensively complex finite difference approaches. Unfortunately, it's very hard to make those formulations, and it's usually left to people who are specialized in the fields, and then computer scientists to program them and keep track of all these basis functions and complicated mathematics. Unfortunately, the finite volume method itself, as you see, is almost always restricted to very low order. For example, first or second order at the highest. And so a finite volume method might be simple, straightforward, physical, and not produce the so-called weak solution like the Galerkin or finite element approaches, but it's restricted to low order. That means to find the equivalent accuracy solution as a finite element approach, many, many, many more volumes in a finite volume solver would have to be used. This is a disadvantage of the finite volume approach. A major advantage of the finite volume approach over other approaches will, of course, be that it conserves all the variables we're solving. It'll conserve mass, momentum, and energy throughout the global domain and locally, because it's strictly enforced and directly accounted for through the fluxes of neighboring volumes. This is exactly what you've done in a simplified way for a single volume element in your fluid dynamics classes. Next time, we're going to turn our attention to something else. We have talked up to this point about discretizing the domain spatially, that is, discretizing the spatial derivatives of structured and unstructured domains using the three most popular approaches. You might now be wondering, well, how do we account for steady solutions or unsteady solutions, because we have not discussed explicitly the time derivatives. And we will first define and understand the differences and important implications of steady versus unsteady solutions. Then we'll look at unsteady solutions and discuss the idea of time integration of the equations in motion. That is, how do we advance in time and observe how the flow evolves, as we do in nature or in engineering problems. We'll further divide the time integration methods, or time marching or time-dependent methods, that is the unsteady ones, with so-called implicit and explicit schemes. And we'll look at some of those formulations based on simple discretization of problems like we did today with finite element and finite volume. Thank you very much for your time today. I'm your professor, Steve Miller.